So now that we know what an exponential expression is, we can say what an exponential function is. An exponential function is one that contains one exponential expression, then a number multiplied by it, and maybe a number added to it. Note, maybe we're multiplying by 1. Maybe we're subtracting 0. Maybe we're adding 0. The simplest sort of exponential function is just f of x is some number to the power of the variable. We only define exponential functions for b a positive number that is not 1. Why is that? If b is a negative number, the filling in the gaps part for defining irrational powers doesn't work right. Why? Because defining rational powers of negative numbers is awkward. Remember, we said that a rational power of a negative number is defined only if the denominator is odd, which is just awkward. If b is exactly 0, then b to any positive power is 0. So the function is constant when the power is positive, undefined when the power is negative. That's boring, and that doesn't have similar behavior to other exponentials. And if b is exactly 1, the function b to the x is just constant. Right? 1 to any power just gives us 1 back. So for b negative, 0, or 1, exponential functions just don't work right. We only define them for b a positive number that is not 1. Let's see what the graph of an exponential function looks like. We'll start with a very simple one. F of x is 2 to the x. I'm just going to put that into the calculator. 2 to the x graph. And we see a function that makes a nice curve increasing. Look at what it does off here to the left. It looks like maybe it's sitting in the x-axis. But let's think about that. Is 2 to the x ever going to be 0 or negative? Certainly, if x is a big positive number, 2 to the x is going to be a big positive number. What if x is a big negative number? What if we want to take f of negative 200, right? That's 2 to the negative 200, which means 1 over 2 to the 200. That's a very small fraction, right? But it's not 0, and it's not negative. Taking large negative powers gives very small positive numbers, as close to 0 as we'd like. So that means this graph here isn't sitting in the x-axis. It's just getting very, very close, never quite getting there. How do we describe this situation? We see the graph of 2 to the x has a horizontal asymptote in the line y equals 0. When we're drawing this graph, so here we have a set of axes, and here we have a horizontal asymptote lying in the x-axis. Now, let's think about what points might be on this graph. We see that when we have negative values for x, we very quickly get very, very small decimals. Right? Maybe you notice that negative 3 gives us an eighth, negative 2 gives us a quarter, negative 1 gives us a half. 0 gives us 1, of course. 2 to the 0 is 1. 2 to the 1 is, of course, 2. 2 squared is 4. Again, we can see that in the table. 2 to the third is 8. So if we want to sketch this graph, well, I don't really feel like I can draw an eighth. A quarter is already pretty small. I can draw a half pretty reliably. I can certainly draw 1. I can certainly draw 2, and 4, and 8. Nothing any bigger than 8 is going to show up on my graph, though. So when I graph this, I'm going to draw a smooth curve going through these points, and then off to the left, I'm going to draw it continuing to get smaller until it pretty much merges with this asymptote. I'm not going to draw it crossing the x-axis, and I'm not going to draw it curving back up. Okay, so that's 2. Let's see what happens with some other graphs. Let's take a look at the graphs of these functions. I'm going to graph the first one in magenta. Notice when I'm putting x minus 3 in the exponent, both of those are superscript. If you have a calculator that doesn't superscript the exponent, you may need parentheses around x minus 3. See if your graph looks like mine. I'm going to graph the second one in blue, and I'm going to graph the third one in red. Notice, I'm not putting -2 in parentheses, so this means take 2 to the x power and then make it negative. This negative sign means multiply by -1. So let's look at these 3 graphs. We see that the pink one has basically the same shape that 2 to the x did, only moved up and shifted a little bit to the side. We see that the blue one has almost exactly the same shape as 2 to the x did, except flipped over. And we see that the red one looks like 2 to the x, but upside down and maybe moved down a little bit. So shifted upward has to come from this +5, and then a little bit over comes from this -3. Oh. For the 1/2, yeah, multiplying by 1/2 is going to give me very, very small numbers. It's negative powers of 1/2 that are going to give me big numbers. Obviously, this negative sign is responsible for the third graph being flipped upside down. And then the -1 is responsible for the downward shift. Okay, I think that we're ready to make kind of a general description of what the graph of an exponential will look like. So in general, the graph of f of x equals a times b to the x minus h plus k always has a horizontal asymptote at y equals k. That is, where the exponential expression would be 0. Now, the exponential expression is never 0. If x minus h is a large positive number, then this exponential expression is a large positive number. If x minus h is a large negative number, this exponential part of the expression is a very, very small positive number, very close to 0. But it's always positive, but it gets as close to 0 as we might like. If the coefficient is positive, including being just 1, the graph is going to live above the asymptote. If the coefficient is negative, including being just -1, so just a negative sign, the graph is going to live below the asymptote. If b is a big number, if it's more than 1, the graph gets big to the right and near the asymptote to the left. If b is between 0 and 1, the graph gets big to the left and near the asymptote to the right. And then if we want to graph more carefully, we can plot the points where x equals h and x equals h plus 1 to get more details of the size and position. But from a very general perspective, there are 4 possible pictures we could have. We could have a picture that looks like this, where a is a positive number and b is bigger than 1. We could have a picture that looks like this, where a is a positive number and b is between 0 and 1. We could get a picture that looks like this, where a is a negative number and b is more than 1. Or we could get a picture that looks like this, where a is a negative number and b is between 0 and 1. And just being aware that these are the general shapes of graphs of exponentials is actually more valuable at this point than being able to draw carefully constructed graphs of individual exponential functions.